Hello everyone, welcome back. Our discussion on the structure continues today. Last time we talked about various structures and their stability and how to draw and how to look at them from different perspectives and how do you represent them in various forms. Some of them are like Newman projections and Fisher projections, and so on. There, we have 6-membered rings, and they're facing each other. At the top, they look nearly perfectly hexagons. But if I turn, like we did last time, they turn into chair conformations. So I'm trying to show these two to begin our discussion today. So please remember this. I cannot hold both and write, so please remember this. So as you imagine a plane that cuts the molecule in half, that goes through hydrogen, carbon, carbon, hydrogen, and this hydrogen as well. So right here, it turned molecules, this molecule, and turned the atoms, and some of them, like these, are above the plane, and those two carbons are below the plane. So you can draw these two lines and these two and the parallel lines to connect them. Then you have axial, equatorial, axial, equatorial, axial, equatorial, axial, and equatorial, axial, equatorial, equatorial, axial. And the other one over here, from this angle, you can see it is kind of mirror image. And you have these two parallel lines, split the angles, then connect, then you start adding the hydrogens. Axial, down, axial up, axial down, axial up, axial down, axial up, equatorial up, on the carbon where the axial was down, equatorial up, then equatorial down, equatorial up, down, up, down. Then if you look at any carbon on the ring, they should be tetrahedral. So around that carbon you should have two solid lines representing parallel to that imaginary plane. That's for your perspective, and they are on this carbon, this line and this line. So these two. Then, as I said, these two are right on the imaginary plane, and those are above. That means this line from this guy is coming out, from this guy is going in. So from this perspective, your line here is going away from you. Then you have this one coming towards you. It's coming out of the paper. So when you see this line drawing of the cyclohexane, you have to look at each carbon and able to imagine each line this way and practice that. Then, potential energy wise, this process is not favorable, but it does happen. Depends on the given kinetic energy by temperature. So the structure can go to the boat form, and these are close and pseudo-axial, pseudo-equatorial. Then other axials and equatorials that are eclipsed, making the structure unstable. And then you need to imagine them better. So let me show you with a model. So this molecule freely rotates every single bond using heat energy. So you can rotate, then some of the axial, like this one or this one, turning into the equatorial, and the equatorials here and here turn into the axial, turning the single bond. If I repeat the motion from this perspective, okay, where you can see the Newman projection, I simply push up this one, turn this equatorial to the axial. You can see turning around this carbon here. So see the turning, right? If I flip back, it turns again. So that motion was flipping this carbon up or down. So as soon as I flip up, you see these are getting quite close and they repel with the same charge, and this side now flip down and come back to the other form of chair through the formation of the boat. So you should be able to imagine these things with the pictures. So this end, when it flips up, goes to the boat. That makes this end flips down, then you form this one. That can happen for this carbon too. This can flip down, then the other one over here can flip up, and you get the other form of chair form. It can happen for every single carbon, basically turning, make the single bonds rotate, and that's the conformational change. Other thing about this structure is the two positions, the axial one here, here, and here, has the same type of interaction that I'm about to point out for these axials down here. And those 6 axials are compared to other 6 equatorials here, here. So when you have the same amount of charge on those positions instead of hydrogen, the only factor making them less or more stable is the distance between them. Say they are same charge groups. If you have them here and here on 2 axials, then the distance here is compared to the distance for the equatorial to other neighboring groups, such as you think this gauge location is quite close, but if you think about it from the side, this is not that close. So let me measure. The gauge position of both equatorial is this much. Same for the axial, neighboring axial from that equatorial. Equatorial to equatorial, equatorial to the axial, they're about the same distance. But that distance compared to the axial You see, it's a little longer, right? So the axial to axial is shorter. That means if you put any significant charge, same charge, they repel more on the axials. If you put opposite charges, then they prefer to be on the axials. If you put big CH groups, they repel the same kind of CH groups, so they wouldn't prefer to be on the axial, they go to equatorial. As soon as you put it on the axial, this will be pushed away and then flipping process starts. Okay, what I just described was on the paper with your own drawing. When you intend to put something on the axial that can cause repulsion, the molecule will have high potential energy, so they wouldn't like it. Then you will experience forces pushing the group away by pushing it down. Then the axial will turn into the equatorial, and this line will push it down. Then this will turn into the axial. However, if neighboring group on the axial is attracting this guy, then it will stay. Therefore, if you want to minimize the energy by pushing away same charge from axial to the equatorial location. It will push down, then the equatorial will go down to the axial. So that's not the real drawing. If I show you on different drawing, say you have that group there, and that's the perspective you can get using the same molecule. If you just simply turn, say this was the group, if you simply turn, you can get this perspective. It's basically the same thing. Just try to show you the changes better. So by a certain group on the axial, that's always happened to be on 1, 2, 3 position, 1, 2, 3 position, or 1, 2, 3 position. So those 1, 3 diaxial repulsive interaction with the same charges, making the bigger group pushed down, this one pushed down, meaning this whole carbon is pushed down. That's flipping that I explained earlier. Then it goes to the flipped half form of the boat. Then that was right here. Then you know you have a group here. So you have the big group here, and you pushed it down, made a boat that brings this hydrogen too close to this hydrogen, depends on whatever you have here, and you cause repulsion, so this thing will be flipped up. Okay, if I demonstrate same way that you can imagine with this molecule here, that's when you have a big group over here. Let me replace this one with a different color, because questions will be given with this perspective. So let's see, you can imagine that this axial one, as you see, they're now pretty close. So the axial is not preferred, and this guy, say, have same charge, and it's pushed down. So as I push this one down, the axial one, it will go to the equatorial by turning other groups. Then the equatorial used to be, this hydrogen now is an axial. And that's kind of, if I turn a little bit, is boat form, right? It's boat form. So that causes this side, the opposite side, due to the pseudo-axial interaction, push up the ring. So now you have a flipped structure, and this guy is now on equatorial. The equatorial gives them more distance, as you see, compared to the previous one on the axial. If I go back, they're pretty close, as you see. So they released repulsive force, then the structure becomes more stable. However, the interaction was attractive, they would stay as axial conformation. Alright, so next step for you to grasp the concept and approach the problems is when the literature or exam gives you this kind of notation. Then what would you do? Well, first I would suggest to look at the groups, because the ring itself would prefer chair form, but it all depends on what kind of attractions and repulsions you have for the side chains. So those side chains, as you see, they are same kind of CH functional groups, so they would repel. Then the repulsion causes the big group and the bigger group to go to equatorial position. So you have to know the ethyl group, the bigger group, will prefer to be on the equatorial over this guy, CH3. So first you would put stable framework. Then you copy the information given exactly the way it is. So let's say you start numbering the ring to find the location to put these two groups, starting from the bigger group. 1, 2, 3. And I just went counterclockwise, and I hope you can see this from this drawing. This one is when you see the molecule from the top, and that one's from the side view. Then on this side view, these lines are coming out of the imaginary plane, and those lines are going into the plane, behind the plane. That means when you assume, say, this is 1, then counterclockwise is going this way. So you get 1, 2, 3. If you choose this one to be 1, which is the same because you can simply turn this molecule slightly this clockwise, so 1, 2, and the 3. You can put that one as a 1, then 2, and the 3. And they are anyway exactly same. So say this one was a 1 for you, 2 and the 3. Then on carbon number 1, you should know what are other 2 lines that you have to add. First, you see this solid line parallel to the imaginary plane, so you have to have another one going up. Then that one's going away, because these are out above the plane, that's on the plane, so the line is going in from this guy, meaning there's another one almost overlapping that's coming out. That has to be parallel to this guy. Then you judge which one is pointing down from your perspective, which is slightly above the molecule around here, close to the camera. So that means the equatorial is pointing down. That's where you put CH2 and CH3 big group. That's a better. Then the other one, axial, is just the hydrogen, which you don't have to show. Then you find the 3. For 3, let's say you can imagine what's up. For 3, going up to you is axial. So the unstable location for the big groups. But that's better, because if you flip this molecule, let's practice. You flip this side down. Then you make a boat with this one on the pseudo-equatorial, then the equatorial one here will push this hydrogen, which is pseudo-axial, then making this one flip up. That makes this one turn. As this go up, this come down, and it goes down, so the equatorial becomes axial, axial becomes equatorial. So you will get that you should have practiced this drawing and recognize the locations quickly, like a fraction of a second. Your number 1 is still here. 2 and the 3. So the flip made this one come down. You can demonstrate the motion with a model, and this one came down as an axial. There you have a group. Then that axial go to the equatorial as it comes down, like this much. Then there is a hydrogen. So this big guy running into all these axial hydrogens by these big groups, and you're going to have a lot of repulsion, so they would prefer go back. This one to the equatorial, that one to the axial, by turning, flip back. So you will come back to the equatorial, and the smaller but bigger than hydrogen still has some steric. However, that's better. So this is the most stable conformation for this compound. There, I made the model of that molecule. The red ball represents methyl group, and here I have 2 carbon chain as a side chain on the equatorial. So that's the most stable conformation for it. So the closest interaction for a methyl group, as it have a free rotation at the given temperature, see the distance, they're closer than normal axial distance. But if you flip the methyl group down because it's close, then you end up flipping this one that's pointing up, right? You push it down, go to the boat by turning side groups. Then you see these two come closer, so I have to push this one up. Then you notice the ethyl group going down from equatorial to the axial. It doesn't go too close, then it causes repulsion, it stops some point. So yeah, axial, this one came axial, and this went to the equatorial, a little better for himself. But if you flip and observe the other side of the ring, ethyl group is on the equatorial, axial, then this group have a free rotation around this attached bond because it's a single bond, and you see the sound, they are actually hitting each other too close. They're like merging. Therefore, this will be repelled back down and pushing the other ends up, and that brings the methyl group on axial. As you see here, it's on the axial. Now the ethyl group is on equatorial. As I show you the rotation, no group is bumping into each other, so you can see you gain the more distance between same charge group. So this one's better. And how do you show this with a Newman projection? That's another thing you have to think about. So when you have this molecule built this way, you can see Newman different ways. You can see from this angle. That means from this angle, a person from this angle will see those two and line overlapped as a one Newman projection circle, and across the ring you have other two carbons. So if I turn it to show you as if you are the person, it will be, I'm holding, okay, will be something like that. I hope you remember the two circles representing two front carbons, having two behind carbons here. They are connected by this one up, this one down. Or you can also see from different perspective something like this. I didn't make any change on the molecule. This way, that's the same conformation, same compound. Then you can see the carbon here holding methyl group on the axial, straight going up as a front carbon, and there is a behind carbon. And this front carbon on the other circle of the Newman has ethyl group on the equatorial going down sideways, and the carbon behind holding two hydrogens. To me, this one's better to show the changes. So let's try to copy. So two circles, then this CH2 is connected downwards, then you have a hydrogen pointing towards you and the one going away from you. Then there's a CH2 here behind, connected to up, and there's a one hydrogen coming towards us and one going away from us. Then the front carbon holding the methyl group, the big group, on the axial, then equatorial is the hydrogen. Then there you have equatorial holding CH2, CH3, and there you have hydrogen where I'm holding the molecule by. Then if you look behind, okay, you have hydrogen between here and there. Then if I move my hand a bit, you can see the hydrogen peeking through here and here. So you have to sometimes relying on this drawing to come up with this. So let me ask you that I showed you with the model, where do you stand to see this perspective from this molecule? And you should know I'm standing over here looking at it this way. That way I see these and these as circle. This carbon here is the front carbon. That carbon there is the front carbon with a CH3 on the axial. And the equatorial here is the hydrogen going down here. And the carbon behind is behind this one, the equatorial pointing up here, the axial hydrogen pointing straight down, and that's connected by CH2 that's pointing up from this behind carbon, which is this. Then that goes to the downward to connect behind carbon on the other circle, which is this, and that carbon has equatorial up, axial down, up, down. Then you go to the front carbon, which is this guy, having hydrogen on the axial, and equatorial, you have CH2, CH3, and the front carbon is connected to CH2 that connects with another circle right there. That's one of the better perspective of Newman projection. So you should be able to freely draw this from that, or from here to that, and then you can imagine turning this one down, and you can automatically see why you cannot turn the other way. So when you turn down, this will move and that will move up, right? Because it's turning this way. That causes this hydrogen facing that hydrogen and repelling this guy down. But when you turn down, you cannot turn this way because you're gonna break the ring, so this one has to go down. Try that with a model. It will make more sense with it. Okay, I hope you are getting better in visualizing molecules which are not, visible to us. That makes chemistry hard. But if you keep playing with the model and imagining them, our mind will eventually capture those little particles and allow us to imagine chemistry better using those physical matters. Not visible doesn't mean they're abstract metaphysical thing. They are actual material. So just keep up your trying, and eventually you'll get it. That's it for today. Bye.